Okay, so this is going to be the video memo for the third weekly test. Sorry, I made a mistake there. That should be number 3. Overall, the marks were okay, but I think there's still some areas where, as a whole in the class, you're struggling with. Remember, the solvents are critical. You just need to know this. I actually basically all but gave away exactly what it is that we were going to do. This is dichloromethane. Dichloromethane. It is such a common solvent in the labs that this really is one that you just do have to know. And then the reduction of using sodium borohydride, a lot of you got confused, although we had mentioned this in the class. Remember, sodium borohydride, when it reacts, it only reacts with ketones and aldehydes. This is an ester. It's not going to react at all. It's just going to reduce the ketone over there. And that's an important thing that you need to be able to do as an organic chemist, is be able to look at the molecule holistically and see where a reagent will react and where a reagent won't react. And so that was quite critical. The resonance, apparently you guys generally did this quite well. So I'm proud of you. That's good. Make sure that you keep your toes on this. So negative charge delocalizes in from this carbon onto that carbon over there, and the second structure, delocalized structure, would look something like that. And remember that what we're drawing out here, our curly arrows, is just a picture that we are developing. This would have been absolutely fine as an answer, just showing how we get the negative charge onto the other carbon. But remember that the picture here is actually a little bit more complicated, and we need to go and look at our molecular orbital diagrams to understand it more fully. And then, of course, for the carboxylate, it's the same thing. If you could do the first one, you almost certainly did the second one completely correctly. The bases was the question which I think foxed a lot of you, and which is a bit of a pity, but I think you need to spend some time just to assimilate this and understand. Remember, when we spoke about pKa's, as chemists, we naughtily referred to a pKa of a base, which it really shouldn't be, but it just helps us to kind of keep the same language. So something like this, butyl lithium, it's a carbon base, and carbon bases with a negative charge on are going to be sitting at 45, even all the way up to 50 in some extreme examples. So this is about 45. This is going to be the strongest base out of all of these. And then water is certainly the weakest out of those. Ammonia is a base. This is an O-, it's definitely a base, and this is an N-, it's definitely a base. So those two should have really been like the easiest ones to have identified. The difference comes in with the rest of these over here, and that is to remember that your pKa, again, bad language, but of an N- is going to be somewhere in the region of 30 to 35, so it's actually the next strongest base. And then we've got an O- versus a neutral nitrogen. O- is a pKa of 16, so that's going to be the next strongest. This is a fairly weak base. It is basic, ammonia, and so that'll be it's more basic than water. We cover that actually in the class, so that's going to be sitting at about 4. And then the last step was some mechanism. Look, this mechanism that I've drawn out over here is quite critical. You're going to see it again, without a doubt. And what's happening here is that the lone pair of electrons on the oxygen, doesn't matter which one, are adding as a nucleophilic attack. All right, lone pair of electrons, the HOMO is adding to the LUMO of the pi bond over there. It's a nucleophilic attack onto that carbon, and we're going to get a 5-membered ring, so it's going to be an O- because there, and this oxygen is now in the ring, and it has still got the hydrogen on it, so it'll have a plus charge like that. And then there's a whole lot of things that could happen next, but it's actually quite okay just for you to say that going from the one to the other is a proton transfer. If you wanted to, you could have just shown this negative picking up that proton over there, and then that bond breaking, so that both oxygens end up being neutral. All right, so that would have been an acceptable mechanism for it. This is a critical one. Dr. Pelly's going to cover this again with you, so please make sure that you get a good understanding of your mechanisms. All right, I hope that was helpful.